So, what are Java threads? Well, the answer depends a bit on your point of view. But fundamentally, a thread is an execution path of a larger program. So in this example where I have here a schematic view of a Linux process, you will see that there is a common area here which contains the code or the instructions for the program. There is a data area here, which on a Java process will be the heap. And there is another area here where the file handles or descriptors for the process lie. This is the common area. And then a thread will be an isolated entity here, which contains registers for the arithmetic operations. It contains a stack for each method invocation, which will contain the parameters, the local variables of the method, and the return types, and also a program counter. Within this Linux process, you will have multiple of such isolated entities or threads. Notice that each of these entities or threads have access to this common area, which contains the code, the data, and the file handles. So for example, you may be watching this video on a YouTube app running on your smartphone or tablet, or if you are on a computer, you're watching this on a computer browser. Well, that YouTube app on your smartphone or the browser is a multi-threaded program that may contain the equivalent of the following threads. A user interface thread, obviously, which is responsible for rendering or painting the widgets or controls, as well as to handle the user input events. These events will be the keyboard strokes as well as mouse button clicks, and you may have some sort of low-level socket or networking thread which is responsible to encode and decode the remote requests and responses. And you may have some sort of I/O thread which is responsible to, say, service local persistence, maybe user preferences to a local file or database access. Another way of looking at a process versus thread is by looking at this view here, where within a computer you will have several processes, and within each process you will have several threads. The important thing to note here is that processes are isolated from each other. So a thread within a process cannot access the data of a different process. Threads sometimes are defined in relation to a process by calling them lightweight processes. Fundamentally though, at the operating system level, such as Linux, threads are the unit of execution that the operating system scheduler schedules. The operating system scheduler is a critical component of any modern operating system, and its main goal is to ensure that all threads in the computer have fair access to the computer resources, mainly the CPU, memory, and I/O. Within the Java runtime, a thread is an object of type thread. It's got a clearly defined semantics, lifecycle, and API. And this Java object is mapped to an operating system thread. So every Java thread object has a corresponding operating system thread. So after giving these definitions with different points of view of what a Java thread is, let's talk about what are the problems that threads are a solution to. What is the motivation for threads? The chief motivation for threads is better resource utilization, mainly CPU and memory of a machine. A CPU processes program instructions orders of magnitude faster than the time it takes to access main memory, to complete an I/O call, or to get a response from the network, say. So you must find ways to keep those fast CPUs busy. To get an appreciation of how fast CPUs are, consider this. This is sourced from the latency numbers every programmer should know, which was originally created by Peter Norvig, and the links is in the description below. So this is quite interesting because the timescales were converted from nanoseconds into the human time scale of seconds, which is called humanized latencies. So the level 1 cache reference or access is 0.5 seconds in average, or 1 heartbeat duration. The level 1 cache is the cache on board the CPU. Level 2 cache is a little bit larger, a little bit slower to access, 7 seconds, the time that a long yawn takes. Invoking a synchronized method in Java, for example, which involves locking and unlocking, takes 25 seconds, or the time that the average person takes to make coffee. Main memory reference, 100 seconds already, the time it takes to brush your teeth. Now we move from the minute time scale to the hour time scale. And here I have an example of compressing 1 kilobyte with the ZP tool, which takes 50 minutes, or the duration of one episode of a TV show. Now we move on to the day time scale, which, for example, is the time it takes to send 2 kilobytes of data, say a file, over a 1 gigabits per second network. 5.5 hours, or the time of an afternoon working day. Moving on to the year scale, the time it takes on average to read 1 megabyte sequentially from memory, 2.9 days, a long weekend. The time it takes on average to read 1 megabyte sequentially from solid state drive, 11.6 days, or waiting for 2 weeks delivery from an order. And the time it takes on average to read 1 megabyte sequentially from disk, a rotating disk, 7.8 months, almost the time to produce a new human being. Now we move on to the decade time scale, where the average time to, say, send a packet of data from California to Netherlands and back, 4.8 years, the time it takes to get a bachelor's degree. So now that you have a better appreciation of how much faster CPUs are over memory and I/O and network access, consider this example here, where you have a computer that has these 2 CPUs, 1 user, and there is 1 single-threaded program running, say a GUI program. So notice that the program, because it's single-threaded, will be running on 1 core, but the other core 2, will be idle. So you have 50% CPU utilization. If you have 4 CPUs, then it will be 25% CPU utilization, and so on. So all of those cores are there, sitting idle and completely wasted. So what is the solution to this problem of CPUs being much faster than I/O? Is to use multi-threaded programs that the operating system scheduler takes advantage of. Each thread then is scheduled by the operating system scheduler. It is assigned a time slice or quantum, which in Linux is about 100 milliseconds, at the end of which the thread is preempted, and there is a context switch from thread 1 to thread 2, where thread 2 then is scheduled to execute. And then at the end of its time slice or quantum, thread 2 again, it's preempted, and the next thread, say thread 3, is scheduled for execution, and the cycle repeats. Note that a thread doesn't have to necessarily consume its time slice. Why? Because the thread may be interrupted before its time slice ends by, say, another higher priority thread. Another scenario where a thread may not consume its entire quantum or time slice is if the thread, say, makes an I/O call. Typically, when a thread makes an I/O call, the operating system interrupts the thread, preempts it, and gives the CPU to another thread. Another benefit of threads is that threads make it easier to model a certain type of programs by breaking it down into smaller programs. So, for example, you may have a thread which is consuming messages off of a network socket. It decodes the data or the messages and puts them onto a queue. And then there is another thread that is responsible for the main business logic of the program that gets those messages or those requests off of this queue, okay, does the actual processing, and then writes the response onto another queue, which then gets picked up by an encoder thread, which encodes this response back onto the network socket. Now, the benefit of threads is that it is generally easier to design and program synchronous blocking I/O programs using blocking semantics. You have here a network socket and a thread that it's blocked waiting for requests to come in. And then when a request comes in, this thread basically hands over a client socket to another thread to handle that user session. And another request comes in from another user. This thread hands over a client socket to another thread that then handles this user to session requests, and so on and so forth. Another benefit of threads is to allow for responsive user interfaces. On a user interface program, you typically, like we covered before, you have a user interface thread which is responsible for the rendering of the widgets in the screen, as well as handling input events, keyboard and mouse clicks. But suppose that this thread then makes an I/O call, because maybe the user wants to load something off of the database. Well, if the program is single-threaded, then while the user interface thread, is waiting for the response to come back, the screen freezes and the user is not able to do anything. How would multi-threaded help here? Well, instead of having a single user interface thread, we would introduce another thread which will be responsible for handling these I/O requests and then give the response back to the user interface thread. So the user interface thread would build this request. The user interface writes this request into a queue, signals the I/O thread that there is a request in the queue. The I/O thread then gets this request from the queue, sends this request, and while the response is waiting, the user interface can continue to serve the user. When the response eventually comes back, the I/O thread will write the response on the queue and will signal the user interface that the response has arrived. The user interface will then be interrupted, will get the request, and it will populate, say, a table for the user. Now, let's talk about disadvantages. As Neil Postman used to say, technology giveth and technology taketh away. This means that for every advantage a new technology offers, there is always a corresponding disadvantage. In other words, there is no free lunch. So, what are the disadvantages of using threads? 1. It is harder to write correct multi-threaded programs than single-threaded ones. 2. It is harder to debug multi-threaded programs than single-threaded ones. And multi-threaded programs introduce the following risks, which are categorized as safety risks, are risks that may break the program logic. So the program does not behave as it is supposed to behave. Examples of safety risks are race conditions and data corruption. There are also liveness risks introduced by threads, and liveness are problems that related to a thread not being able to continue execution. The most common and perhaps well-known example of a liveness risk is a deadlock, but there are others such as starvation and live lock. And threads also and finally introduce risks of performance. Locks and thread context switches add performance costs.